Okay, so imagine then, let's start today's content with a concrete example. Let's imagine that you guys are the HR managers and you're evaluating two candidates that apply for the job in your company. So the first candidate is Andrew, and he is of a particular major. Doesn't matter what it is. He has his bachelor's degree, and overall, this is his score in his class out of 100. You can imagine this as Andrew's average, right, across all those years of undergraduate schools, 70 out of 100. And the second candidate, Angie, is from a different major than Andrew. And interestingly, in her class, the scoring system is very different from the scoring system in Andrew's class. In Andrew's class, everything is scored on a 100-point scale. In Angie's class, everything is scored on a 7-point scale, and this is Angie's average performance in all her undergraduate years. So the question is, as the director of the HR, who would you recommend the boss or the CEO of this company to hire? Andrew or Angie? And the only criteria, sorry, should be criterion, right? So the only criterion is who's the better student in their own class. Okay, we don't consider extracurriculum activities. We don't consider, who's a better, leader, whatever, right? So we're only looking at the two, their scores in their class, and whoever is better will be recommended. What would you say, Andrew or Angie? That's an interesting question, right? So perhaps you should pause here to think about it and perhaps do a little bit of calculation to make up your mind before I announce the answer, right? So we could say Andrew will be the choice, or we could say Angie is the choice, right? We can have sort of a imaginary vote, right? Who will vote for Andrew? Sort of raise your hand. Who will vote for Angie? Um, Raise your hand. Um, but it turns out the correct answer is we don't know. We need more information. Just using the information that I provided with you just now in the previous slide, 70 out of 100, right? Or 5.5 out of 7, we don't actually have enough information to make a decision. And here's why. Okay, so many of you might think that for Andrew, his score is 70 out of 100, so that means he is sort of at a 70% of his class. For Angie, though, if we divide 5.5 by 7, Angie will be, at about 79% of her class. Okay? Obviously, 79% is a larger value than 70%. So shouldn't we recommend Angie be hired? This is certainly one way of thinking about this problem, but as we'll soon see, right, why you know this piece of information is not enough. We can use the same information to make the exact opposite decision, that is to recommend Andrew, and we'll see why. But let's imagine that Andrew actually comes out from a class whose score distribution is like this. we have talked about this distribution, right? We say this is a right skewed distribution, meaning it has a longer tail to the right and more scores are at the lower end of the continuum, right? Imagine, you know, the the x-axis represent score, right? And y-axis, obviously, it's a frequency distribution, right? Frequency, how many people are, for example, at this part of the score continuum. And we also said in that particular class where we introduced this type of scale, distribution, is that this distribution typically comes from, in the context of examination, right? Typically results from a very difficult examination. In this case, a difficult program. That means very few individuals will be at the top of the score continuum, meaning, very few individuals will have very high scores from this program. Lots of people, right? Lots of the most people are actually clustered around the lower end of the score continuum. That is, most of them actually perform very poorly compared to very few of them performed excellently, so to speak. So if this is the case, right, and if Andrew is indeed at a 70% or percentile of this class, he actually is a pretty good student. Even though 70% does not seem to a very high percentage, we've seen 80 and 90%, percentile. But given this particular distribution, Andrew is in fact a pretty good student, given that most of his classmates actually are at the lower end of the continuum. Now you can imagine where I'm going. We can imagine actually Angie comes from a class whose performance distribution is like this, right? So again, we have score as the x-axis and y as the frequency, right? So in this case, we know that distribution is left skewed because the longer tail is at the left, and most people or most scores are actually clustered at the higher end of the continuum. That means in Angie's class, most people perform very well. Most people have very high scores, and very few people have very low scores. So this is exactly the opposite, right, as in Andrew's case. In Andrew's case, very few people have high scores and most people have low scores. In Angie's case, most people have high scores and very few people have low scores. So we also know that this distribution typically comes from an easy examination, or in this case, an easy program, right, where most people can perform very well, or we can think that most people in Angie's class is very smart. Well, either way, right? That means most people are receiving high scores. So although in terms of value, right, numerical value, 78% is definitely higher or larger than 70%, but there are more, if we understand, this frequency, right? There are more people actually ahead of Angie, right? Despite that Angie is at a higher percentage than Andrew, but there are more people ahead of Angie than the amount of people ahead of Andrew. In Andrew's case, only fewer amount of people are ahead of him. For Angie, more people are ahead of her. So that means actually, if we consider their performance in their own class, Andrew is the better student. Comparatively, Angie is the worst student. So in this case then, we actually should recommend Andrew instead of Angie. Right? So that's our conclusion. If we imagine that, they're from, these kinds of classes. But in my previous slide, I never provided these pieces of information. That's why I said we need more information. And that information is precisely the shape, right? What kind of distribution are we talking about when we look at these scores? Okay. So in our daily life, we're making all kinds of distribution or comparisons like this, right? Who's the better student in their respective class, right? Who's the taller person in their own country, right? Jingguang from China or Andrew from the US, right? So again, right, China and US obviously have very different distributions of height, right? And a person as a tall person, quote unquote, a tall person from China is not necessarily a tall person from the US or vice versa, right? And so we need to consider, right, if we are talking about who's a taller person in their own country, we also need more information, right? What's the distribution of height in China and what's the height of distribution in the US? And also, one took SAT and the other took ACT, two different kinds of entrance examination. Well, who scores higher, right? We can't compare these two scores directly because obviously they're different kinds of tests and their scores have different distributions or are differently distributed, right? So again, we need to do something, or we need to apply some additional procedure to all these cases to make students from different classes, to make people from different countries, and to make applicants taking different examinations comparable, right? And we have many more examples. So, at a more general level, right, whenever we are comparing scores from different distributions, right, better students in terms of examination scores, height, obviously there are scores on the scale, SAT, ACT, obviously they produce scores. So, and we can imagine different classes have different kinds of distributions, right? Right skewed, left skewed, right? And obviously from different countries, we have different distributions for height or any other feature you're interested in. And ACT, SAT, they also have different distributions, right, in terms of their score. So, right, whenever we're comparing scores from different distributions, we need to equalize their metric, right? These scores, they are taken from using different metrics. So, for example, in China, we're using centimeters, whereas in the US, we're using feet, right? Or foot to or inches to measure height. Um, Students from different classes, they may use 100-point scale, some may use 7-point scale, some using other kinds of scales, right? SAT, ACT, they also have different metrics. So in order to make all these scores comparable, right, we need to equalize their metrics. And the equalized metrics or common metric, right, will provide will enable the comparison. Okay. But then of course the question of course is, how do we put all those different scores into or onto a common base? To do that, we need z-scores. Okay. So z-scores, another name for z-scores is standardized scores. And these standardized scores is produced from a process that we call standardization. Okay. So it's like it's an activity, right, or process, and it's a process of calculating z-scores. Okay, so far, we know, sort of understand these names, but these definitions does not tell us much, right? So now we need to understand what z-scores really are, right? What do we mean by standardizing them? Okay, so conceptually, z-scores, or the z-score for a value x, that is for any value, right, What it means is it provides a very critical piece of information about x. That is, the number of standard deviations that x, the value, deviates from the mean of the sample from which x is from. Think about it. Let this definition sink in, right? So z-score, or the z-score for a value, essentially tells us how far away at the unit of standard deviations the x is from the mean of the sample from which x is from. That is, how far away x is from the mean. And we measure this distance between x and the mean using standard deviation as the metric. Because, as we said, standard deviation is the unit distance, right? It's the unit distance for any x, relative to the sample mean. Okay? And of course, then if SD is the unit distance, if we want to find out the actual distance, right, then we should be talking in terms of, x deviates from the sample mean by 1, 2, 3, or 3.5 standard deviations. Okay? So x deviates from, so then how do we calculate? So if this is the conceptual definition of z-score, then how do we calculate the z-score for a value x, right? So we can again dissect this definition, right? If x deviates from the sample mean, how do we calculate the deviation of x from the sample mean? Easy, right? X minus the mean. Sorry, I don't know why there's a y here, but okay, scratch it. Just x minus the mean of the sample from x is from, right? So I means any value or all values. Okay. But then, how do we calculate this part? The number of standard deviations. Okay. So if you think about it, it should be actually pretty straightforward. If this is the distance and SD is the unit distance, then how do we calculate the number of units? Easy, right? It will be x minus mean divided by SD. Then this ratio will tell us the number of how many standard deviation is x from the mean. Okay, it's like we have a certain number of people, right? Certain number of people in the room. Okay, certain number of people. Right? We want to figure out how many people, exactly as we want to figure out how many standard deviations, right? But then we know that there are a total of 100 apples, right? It's like we know the distance, right? We know the actual distance. In this case, we know there are 100 apples. And we also know that each person in this room will have 2 apples. That is, analogously, we know that, the unit distance, that is, we know what standard deviation is, right? Then, given these conditions, right, it's very simple to find out how many people do we have, right? If we have 100 people, 100 apples in total, and each person in this room has 2 apples, then, well, we should have 50 people. Similarly, if we know the total distance of x from the mean, and we know SD represents the unit distance, Then how many units are there? Well, distance divided by unit distance. Okay? So this is the formula for z-score, right? Um, any x, any value from the sample minus the mean divided by the sample standard deviation. We know how to calculate these two guys, right? And x is always given, so we know how to calculate z-scores. So a couple of things to notice, that is, each value in a sample has its own z-score. And only one z-score for each value, right? It's like, each one of you has its own social security number, okay? Unique and only. So that means, if we have 10 values in a sample, there will be 10 corresponding z-scores, each one for, a value. Or if 100 values, then there will be 100 z-scores. Again, each one z-score for each one value. Okay, and z-scores can be positive, can be negative, can be zero. And we can easily find out under what condition the z-score will be positive, because SD, standard deviation, is the square root of something. And square root, if we take the square root of value, it would never be a negative number, right? And it cannot be zero, because zero cannot be the denominator. So this SD will always be a positive value. Then if z value is positive, that must mean that this distance or this difference is positive. That means x will be larger than the mean. Okay. So if we look at look at a positive z value, that means the score must be greater than the mean, right? If there's a zero z value, that means this particular score is exactly the mean, right? Equals the mean in terms of value. And if we have negative z-scores, that means the score must be smaller than the mean. Okay. All right, so let's see if we really understand this. Okay, so imagine that in a sample we have a value that's 4, and I give the sample mean for you. I give you the sample mean, that's 1, right? And the standard deviation is 1.5. So what's the z-score for? How do we convert this value to a z-value, or how do we standardize it? Okay, you should do it this by yourself. How do it is by hand, right? You should pause now and do it yourself. But imagine you have paused and you have got a number, the outcome. Let's do this step by step together. So the first step is find the mean, right? We know the mean. That's 4. The second step is find the standard deviation. We know the standard deviation here, right? And apply the z-score formula, which is z-score equals to x, the value, minus the mean, divided by standard deviation. Okay, so here it will be 4 minus 1 is the mean, standard deviation is 1.5. Okay, so it will be 3 divided by 1.5. Z-score is 2. Easy, huh? Now we can solve this problem. So Andrew has a score of 70 out of 100 in his class, and now we provide a second piece of information for this question. And this class, the overall distribution, the distribution of the performance of all students in this class has a mean of 50 and standard deviation of 10. Okay. Angie, a major of Y, has this average score, and he comes from a class that has a average value of 5 and standard deviation of 0.5. So who's the better student in their own class? What do you do? How do we solve this problem? You should pause now and think about it for yourself. right? What do we do given these extra pieces of information to answer this question? You might have guessed. Well, since we're talking about z-scores, how about we calculate z-scores? And z-scores make sense here because we know that z-score is essentially to standardize standardize the scores from different distributions, right? Obviously, this distribution, right? This distribution is very different from this distribution. They have very different means. They have different standard deviations. But what if, right? What if we can convert these two scores, for example, the 70 score, to the number of standard deviations from the mean, right? That is, we're converting this score to a distance. And if we also convert the score to another distance, right, which will have the same mean and same distribution, same mean and same standard deviation, that will provide a common base for our comparison. Okay, so essentially we're calculating z-scores. So z-score for Andrew will be, that's the value, right? We're going to convert, so that's x, and we know the mean is 50, and we know standard deviation is 10. So what's the z-score? 70 minus 50, that's 20. 20 by 10, 2. What about Angie? That's Angie's score. That's is Angie's class mean. That's his standard deviation. So 5.5 minus 5, that's 0.5. 0.5 divided by 0.5, that's exactly 1. So the z-score for Andrew, which is 2, means that Andrew's score is 2 standard deviation above the mean. Whereas Angie, her score is only 1 standard deviation above her mean. Now, these two values are comparable because they're just simply distance, right? 2 is the distance from Andrew's score from his class mean, and 1 is Angie's distance from her class mean. So these two values as distances can be directly compared. That suggests Andrew is indeed the better student in their own class. So we should recommend Andrew to be hired for the job. Okay? Well, I hope that makes sense. You should, right? As a different exercise that should be rather similar, right? So if Andrew took SAT and scored 650, and we know for that year, the distribution for SAT scores has a mean of this and standard deviation of this. Angie took ACT and scored, and this is Angie's score, and for that year, the ACT has a distribution with a mean of 20 and standard deviation of 4. And they're both applying for UHM. And as you, as the admission officer, who would you admit? So again, right, we're comparing scores from very different distributions. So what we need to do is we convert the scores to distances, right? So we essentially ask, how far away is Andrew's score from the mean? And how far away is Angie's score from the mean, right? If Andrew's score is farther away from the mean in the positive direction, right? So we're considering, okay, so if the mean for Andrew's SAT is here, and if Andrew is here, right? That's Andrew's score. And if we, at the same sort of a position, place the mean of ACT, right? So this is SAT, ACT, right? So if we also place um, the mean for ACT at exactly the same position as SAT, then we can ask, well, how far away is NG score from the class mean, right? So, this the positive distance. So if it is the case that Andrew is further away, way above the SAT mean, the NG score is above the ACT mean, that means Andrew is the better student, better applicant. But if Angie's score is way above the mean compared to Andrew's score relative to the SAT mean, then that will mean Angie is the better applicant. So again, we're converting these two scores, 650 and 28, at two distances from their own mean. Okay, so that means we're calculating these scores. So 650 divided by minus the mean, so 409 divided by 10. What is it? It is 3. That's 4, 5, sort of 553. Sort of. Yeah. Am I right? So it will be 650 minus 4. Yeah, 153 divided by 10. So 15.3, that's the distance of Andrew's score from the overall mean. What about Angie, right? 28 minus 20 divided by 4. Ooh, only 2. All right, so that means Angie's score is above the ACT mean by sort of 2 units of standard deviation, whereas Andrew's score is above the SAT mean by 15.3 standard deviations. Well, obviously, Andrew then is the better student. So you should omit Andrew, okay? Because Andrew is way better than most students taking SAT, whereas Angie is only a little bit better than most people, the average score of ACT. Okay, so Andrew is better applicant if we only consider scores. Okay, so right, okay, so that's from the previous, the job applicant example, right? So if we visualize the z-score, right, we're essentially, we'll soon talk about what do we mean by standard normal distribution. But essentially, we can imagine another way to understand z-scores is we're converting these two scores, which are from very different distributions, right, different means, different standard deviations. We convert them to z-scores so that we can plot all these z-scores in a common distribution, in a standardized distribution. And we call this standardized distribution or distribution for z-scores as standard normal distribution. Right? Z-scores also has its own distribution and it's a standard normal. Okay, so essentially we're saying, well, let's put and convert all these raw scores to z-scores so that we know where the z-scores will fall, right, from the mean. So if the z-score for Andrew is 2, Andrew is here, right? Angie's score is 1 and it's here. So Andrew's here, right? So obviously Andrew is above the mean by 1 more unit than Angie is. Right? Angie is above the mean by 1 unit, whereas Andrew is above the mean by 2 units. So Andrew is the better applicant here. Okay, so that's the use of z-scores. And really z-score is a very, very important concept. So we will revisit this idea, this concept frequently in future classes.